Boing. Okay, springs. What a wonderful topic. This is class 22, and it is the spring of 2019, and we are dealing with springs. A coincidence? Yes, entirely. So, here we go. All kinds of different springs. You got boingy springs. Most of the time we think of them as compression springs, but they could be extension springs. They could be leaf springs. They could be coils. But what they do have in common is they usually have relatively large elastic deflection compared to just regular bars and that kind of thing. Although you can think of just about anything that can deflect and then come back to its original or near original position is a spring of some sort. But generally we're talking about something its purpose is to relate force and deflection. And that can control the motion in machines. It can reduce the transmitted forces between things and absorb some shock and energy. And because it absorbs energy, it's a good storage of energy. And it's also a good measurement of force. So there's lots of different things we could use with springs for. You get a spring in a ballpoint pen. That's pretty common. You could also have springs that are like these flat washers called Belleville springs, where there's like a little concave, and you press them down and they deflect, and they relate that deflection with the force. So you could preload things with these Belleville springs. You can have a torsional spring, and there's all different kinds of different applications where we want to put a torsional spring into things. You have a flat spring. I usually associate these with those little wind-up toys, or you could have like a wind-up clock, that kind of thing. And those are energy storage devices. You store up some energy, and then it releases it slowly. You have leaf springs, so there's these flat plates together, and they form the spring that goes underneath the suspension, usually in the rear of trucks. Extension springs, so we don't just have compression springs, we could also have extension springs. We have torsional springs, like this is a clothespin, I believe, or you might have a rat trap. There's another flat spring. I have like this drawbar spring. I have one of these connected to my dog's runner, the cable, where she runs back and forth between, it's connected to a tree in the house, and she tries to see if she could pull that tree down and the house down. And there's a constant force spring, and I've never had one of these, but it's kind of interesting type of idea, because usually we have a slope and the force changes and increases with the amount of deflection, but apparently somehow you're able to have a constant force spring. And just various other types. I don't know, there's some repetition right here. So things that we want to know about springs can include the physical constraints, like the range of the motion. There's a limiting to like the solid length. There's also the inside and outside diameter. These are important things. You might want to fit around something or fit inside someplace. Those are kind of limits or things that we want to consider. We also have the spring rate. That's an important thing. That's our all-important K, right? So that's going to, that's force over deflection, and usually, a linear relationship between force and deflection. K is the slope, right? But we don't necessarily have to have a linear relationship. It could be various other kinds of behavior that could take place. Like they call this one stiffening, and they call this one loosening, I guess, or softening, maybe. I think it's what it's called right there. Is that right? No, the other way around. This is stiffening, right? Because the slope is getting more as you go up, and this is softening, right? But most of the time we have a linear spring, nice straight line. It's just a slope. And other things we want to care about are the stress in the spring. We talk about static loads. We could also have dynamic loads, but most of the time we're looking at, we will do calculations in static. We want to know the strength of them, and therefore we want to know a safety factor. And we don't want to know some kind of load limit. So these are the kinds of problems you get asked. We also might want to know the critical frequency. So the spring has a mass, and it has stiffness. So if you were to put a load on it and it was repeating with time, and it was sympathetic in it, the frequency of this was in resonance, the spring could get all boingy on you and go crazy as it got into resonance. And the idea there is that a lot of that you could relate or one way that you can relate and think of the resonance is the speed of sound throughout this spring. It can travel with a certain speed, and if it gets, and well, of course, it will reflect back and forth. Well, if the reflection and the input, they were to match each other right there and bombard each other, they would have to bounce back away from each other, and therefore you get like resonance. That's like a simplistic way of thinking about this, but you put a knock on there, and then there is a wave, that is cascading down along the spring, and then it could bounce back off of this surface, and you could have that interaction, could cause resonance. But that's the idea, that mass and that stiffness determine the speed at which that wave will travel. And then that's how you get sympathetic resonance, when you match that speed. And then we have stability, which is buckling, right? So you could this could be long, tall, and it could be slender, and therefore it could buckle whoop, bloop, 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 out of shape, right? So we have to be mindful of that. And then we can also worry about fatigue safety factor, right? We might want to concern ourselves about when something is going to break, a spring is going to break after it's been in service for a while. For physical constraints, one of the primary things that we're going to run is the number of coils. And the counting of the coils. Here they show that these are 7.5 coils that are part of that, but we have to think about how many active coils there are. That's another part of the constraint. So there are the actual physical number of coils, and then there's the number of active coils, and we'll talk about that in a second. There's also the big diameters. You got the outside diameter, the inside diameter, and then you have the wire diameter, or little d. So we use big D to represent the mean diameter, dm, right? Or we just use a D, really. So anytime you just see a D alone, they mean the mean diameter. That's the one that you use for most calculations, and that's going to be the outside diameter minus 1 and only 1 wire diameter, right? So that makes sense. Because the mean would be like you'd be subtracting 2 of 1/2 of the wire diameter. Therefore, it's just the wire diameter. And there's a really important parameter that we're going to use with that mean diameter and that wire diameter. And that right there is the spring index. So it's like a good non-dimensional term that gives us sort of an idea of some of the behavior, some of the properties, or the category of springs. And that's a number that's usually somewhere between, about 4 and 12, maybe even down as low as 2 and 12, or 2 and 14. Somewhere in there, that ratio between this mean diameter and this wire diameter. In other physical constraints, we worry about the free length of the spring. And then we also consider the installed length, right? So you're going to, this thing is by itself will be sitting around and being all nice and happy. But then when you put it into something, you need to give it a little bit of compression right in there, just so that it doesn't go bouncing around. And then you're going to probably have like an operating deflection, like it's going to be put into service and it's going to deflect even more away from here. So like here's like the operating range that you would have right in there. Right, it would go in between the installed one and while the thing is working, and fluctuate maybe inside there. And then you could go down even further and go to the solid length, and that's when the wires are touching each other, right? So let's see, I guess I will keep this, and we will put the camera on here. I guess I gotta write this because it's in what do you call it? How come you're not doing this? Come on. There you go. And I want to put the camera on and show off some springs. Like, okay, so here is a spring, right? And it's got its free length right here. And you want to crush this thing. All right, so you install it, right, so into a string, and then you have like it can only go down so far, and now you can actually see buckling happening, right? It wants to buckle outwards, but now you could crush this all the way down to its free length, That's not necessarily easy to do. I'll be using this camera again here in a second because we have a couple other things we want to talk about. All right, so coming back to springs. And here's a little animation right there from some dude named Doug Wright. He made it 20 years ago. Hard to believe 20 years have passed. And you can see that here's like the working range right in there. And it actually given this name in between the solid length and the lower limit of the working range, calling that the clash allowance and solidity limit. That's interesting. Right. So anyway, you could kind of get a sense of this operation here on the force versus deflection graph. And stresses in springs. This is an important thing. So I'm going to do the derivation here that I didn't do in class. Right. So we take the stress that's going to happen within a cross section by taking our spring and just lopping it off somewhere along the middle, and then taking our FBD of it. And if we were to take the sum of the moments about, let's say this point right here, right, that's fine. What we would find is that we would have F that's happening right here there would be some kind of torque that would be placed onto the thing, right? And so the torque that would be placed onto the thing would be that would be the counterclockwise one. That's the reaction torque, and then this force times d over 2 to be able to equal 0. So the torque that's happening, it's inside, that's being felt by this cross section, is equal to F times d, which is the mean diameter, over 2. We could beat it by that. So we know that a stress that we would experience is that torque TR over J. And then someone has placed another diagram over here to tell us that we're not done yet. It could also have a shear, right? Because if you have a cross section and you put a force in line with that cross section right there, you're going to have a type of stress. Now, we know that we often would use for transverse, we would use a certain amount. We would put like 4/3, I think, for a circle. I think that's true. Yeah, I believe it's 4/3 for a circle. But let's just treat it as like 1. Let's just say that it's going to have those two things on top of it. And so this is torsional. And this is, we could call this direct shear, which we usually do the F over A for direct shear. And down here, someone has made a little diagram and shown you that when you add these two things together, that on the inside surface, right here, the torque and the torsional shear and the directional shear, they add together. Now, how do I believe that? Well, they're actually showing this in probably the other. They're probably showing it for over this side right here. But let's look what happens right here to two little stress wedges. The torque, if it's going this way right here, makes a shear that goes that way and a shear that goes that way. We're talking about this cross section right now. And then, but if you also include the direct shear, that's going to be upwards in both of them, right? So it's the inside surface where these two stresses, the two types of stresses, are going to be the maximum. And if we go and we start manipulating this, we could do some substitutions. We know that T is equal to FD over 2. We also know that the radius, the R that we have right up here, that could be the wire diameter over 2, right? And if we were taking the J, we know that that's pi D fourth over 32. And then also know that the A is going to be pi over 4 D squared. So we could substitute all of those things into the above relationship here, right? The tau was going to be equal to, did I do the algebra here? I guess I didn't do the algebra. Shame on me. I think, I should have done it. Yeah, I kind of wish I did, but I didn't. Okay. So we had the 32, and there's a 2 and a 2 and a 32, and what we're left with is an 8, right? And then F big D over pi D3, right? Because we had a D4 right here. We also had a D right there, so they got rid of those. And then we also have over here, this is a little easier, 4F over pi D4 squared. Yes. Did I do that? Yes. Okay. Now we could do a little bit of algebra here. And we could pull ourselves out and go 1 plus little d over 2 big D, 8f big D over pi d cubed, right? Because we needed an extra d over there on the area one on the direct, right? We needed an extra d, so that's where that d comes from. And we also needed a big D over here that wasn't like over on this guy. So that's where we get this, to get these two things to match up. And this, we give this a name. We call this K, big K, not little k. Little k is the stiffness. This is a coefficient, big K. We call that big Ks, right? And just to mess around a little bit with this stuff, we use the spring index. Remember, the spring index was big D over little d. Well, we can go ahead and we can put those things into place by saying this big Ks is equal to 2d plus little d over 2 big D, and divide the top and the bottom by little d. And if we do that, we find we get 2c plus 1 divided by 2c. So that's what this Ks is going to be equal to. So what this K, we could think of this Ks as like a correction factor. What is it correcting for? Well, it's kind of correcting for, if we're looking back over here, right, we could see that this right here is essentially the same thing as this equation. But this Ks is really correcting for the fact there's also direct shear. But there's also other things taking place. There's also stress concentration. There's also a little bit of an issue that we're actually dealing with a curved section, right? This thing has some curvature to it. So it isn't just a straight rod, which maybe would behave the way that we're pretending it is when we're just looking at a cross section here. That's got some of that curvature. The inside's going to be treated a little bit differently than the outside. So that curvature effect increases the stress on the inside, but decreases on the outside. And so there's different factors. There's these competing factors. Well, first off, Ks is the one that we just used, right? So that is not, that right there is just math, right? And so that is a shear correction factor, though, is what we consider that to be. There's also the wall and the Bergstrasser. And I don't know if I've written down or if it matters enough to write down what these other competitors are going to be. And why did you go into another section here? Where did page 2 go? Where did you go? Page 2. Okay, page 2. There you go. You jerk. All right. And so anyway, the only one we care about is the Bergstrasser. And that looks a little bit like the one that we just dealt with, but you can appreciate that these things vary by the spring index. That D over D, that ratio right there, has a controlling interest in the way that the stress works. So this ends up being equation 10.5. And we apply that into our go-to equation for stress, which is KB, and then we have our 8F big D over pi little d cubed. And this is equation 10.7. Mind you, that big D, remember, that is going to be the mean diameter, right? So this is like an important equation number 1. Now, here's a pretty picture of a spring. And here's me making an FEA. And you can see the results of the FEA. The spring, the stress is largest on the inside. And then I took a little slice out of the thing. I sliced it in half so you could see it in motion right there. So you can kind of see through its cross section. So like can I pause this in the right spot? Nope, I can't apparently. You see right there, you can see that it's got all that stress on the inside, maximum right there. All right, so the other thing we care about in springs, one of the purposes of our springs is to get some deflection, right? And we want to know the relationship between force and deflection, and that is our spring rate. And what we do is we use strain energy as the concept, because that's one of the things that springs are. They store energy. So on a force versus deflection curve right here, a typical spring is linear like this. And if we were to take a particular point, like we would put this is the force and this is the deflection we're putting on here, right here, the area underneath this represents U is the strain energy, a 1/2 F del, right? It's a triangle, so it's 1/2 right there. And we'd also find that that we also know that K was AE over L, right? I think I've established that before when we're talking about a bar that's in tension, right? We'll recall that could be found from the fact that we could find our our strain is del over L, and our stress is equal to F over A, and we know that stress and strain are related by Hooke's law, right? So just putting those guys back in there, we were able to rearrange, and knowing that K is equal to F over del, we get AE over L, right? So for that simple tension type of situation right here, we're able to find that that we can get the strain energy now. We could replace this del or F, maybe you could say. We could replace it back into there, and we could find that U is going to be 1/2 F squared L over AE, right? All we have to do is say that these two things right here. We could say that therefore that F is going to be equal to no, I'm going to go, sorry, let me take that back. I go del, what the hell's wrong with me? Del, it's a long list, is equal to FL over AE. You stick that back into here, and we're stuck with this. Okay, so we all agree that's the strain energy that we could do, put into the thing. Well, one relation. Okay, so here is one version, but we could also do the same thing for other types of loading, right? We could have torsion, right? So that's going to be TR over J, but we know that the deflection is going to be the theta over the length of the thing. It's the skew of the thing. It's got we also know that G is a strain, is that torsional strain. It relates the angle of the torsional strain to the torque. So we could play that back in there. So we get the same thing. We're doing the same thing as up here. And we could do the same thing for direct shear or for bending or for transverse shear. So if we have a much more complicated piece, like we do when it's when we have this curvature, this curved coil, and we want to try to find the thing, what we could do is we can do this as an integral, right? So now that this thing changes with the increments as we march along the coil, right? As we're going along the coil, we can figure out on a linear distance along the thing, we can find out what the energy is, and we can find the total energy by integrating it. Well, it turns out Castiglianos Theorem will use that idea, And the basic idea, I mean, it's the simplicity in itself, right? That if the strain energy, right, is going to be, or a little increment of strain energy is going to be F times D del, right? So for every incremental amount of there, then it would say that, like, okay, well then the deflection is going to be the partial derivative of that U with respect to the partial derivative of a force. So we set the thing up in this way, and we're able to find what the deflection is. We're able to calculate the deflection based on the strain energy. And the usefulness of this, even though it seems like it's a rhetorical type of statement, is that now we can calculate a much more complicated scenario than just a little bar or something. So a spring actually has two parts. It has T squared L over 2G J, right? That's going to be this guy. And then it also has F squared L over 2AG, right? So that's going to be the direct. So what you want to do is you want to substitute the things, right? We want to substitute. And maybe I want to give myself a little bit more room here. So I'll end the show, but I'll keep this. And we're down to here, right? Let me move him up. And also we'll move him up. And what does our time frame look like? 26 minutes. Too long. Maybe we ought to end this and start a fresh one there. Well, we will for the example. Okay. No one's going to watch this anyway. I'll just watch the examples. But you might care. You might give a rat's ass. Maybe we will make do some kind of guitar thing to reward those who actually are listening to this kind of stuff. We want to substitute into this equation that we have for the strain energy that the torque is equal to F times D over 2. Substitute in that the length of the coil, or the length of the spring, is going to be pi d, that's the circumference, times n. That's the number of coils. And let's only use the number of active coils, right? You get that, right? That this is, we could say, well, if we stretch the whole thing out, here's the circumference and then the number of coils that you have right there, right? That would end up being what the total length of the thing right here that you would have. And then J is, we know that's going to be pi over 32, D fourthed, and then the A is going to be pi over 4, D squared. So if you plug all this happiness into this, you get, I'll write it down, 4F squared, right, okay, D cubed NA over D fourthed, big old G, plus 2 F squared D NA over D squared G, right? So we got a lot of things in common right here. If we want to find, let's say, Y, right? So this is really the deflection, really. I don't know why I'm just calling that Y. We want to take the partial derivative of U with respect to the force, which is pretty easy to do right here, right? Because all the forces are just right there. And now we're just left with 8FD cubed NA, and then D fourth G, and then plus 4FDNA over D squared G. And then you do some manipulation right here. You go 8F cubed NA. Whoop, where'd you go? Not cubed. Here you go. I jumped over a letter. D cubed NA divided by D fourth G. There you go. 1 plus D squared over 2D squared. But that's interesting right there, because remember that C is equal to what did I say? Big D over little d? Yeah, big D over little d. So this guy, he turns into 1 plus 1 over 2c squared, right? So we know that c has a range of 4 to 12. And when that's the case, this part right here has a range of 1.031 to 1.003. So therefore it's negligible. And so what we can say, what we're left with, is that y is approximately equal to 8f d cubed Na over d4g, and we do know that that was supposed to be an f right here, that k is equal to f over, and I said y here, I don't know why we meant y, over del. So k is, and they use like a little approximately, you'll notice there's a little bit of a, I think they use something like that, kind of like a little thingy in there, but we just go ahead and say d4g over 8d cubed Na. And that's equation 10(9). You know, it seems to me that this is, even this is not that complicated of a problem that you would necessarily need to use this Castigliano. I want to emphasize, though, that energy methods like Castigliano are important concepts in all kinds of engineering fields that you want to try to get involved in, or you might get involved in. It's a go-to way to try to solve problems. All right, so that was a lot of happiness. I almost think I should end the recording right now because I don't know. I talked a lot about the things that we would care about in class. I think this is important. Let me start a new video here. That's a good idea. All right, so we'll end this one right here. And we'll just call it lecture or derivations part 1 or something. I don't know. Yes, discard all that nonsense. I don't know why. 30 minutes is too long of a video.